about permutations and combinations. So a permutation, the way that we're going to define it here at least, is going to be, this is the thing that order matters for. So it's an arrangement of some or all of the elements from a given set in a definite order. Okay, so this is where order matters. We're looking at a subset. We're using the elements. How many ways can we arrange them or set them up? So let's jump into an example. Suppose that we have 7 books to choose from. Okay, and what we want to do is we want to know how many ways can I arrange 3 books from these 7 on a bookshelf. Okay, so that means that often when we have permutations, we're looking for putting things into buckets, right? And I use the word bucket just to mean you have these categories, you want to put stuff into them. So here we're arranging 3 books, so we have these slots. Okay, so we have 3 slots for these books. And I want to know how many ways can I arrange these 3 books. So in my first bucket, I have 7 books to pull from. So I could put any of those books in this spot. So I have 7 options here. In the second slot, I've now put a book into the first slot, so I only have 6 books remaining. So I can put 6 books in the second slot. And in the final slot, now I'm down to 5 books. So based on this, I can just multiply these things together, and this is going to give me 210 different ways to arrange books. Okay, this is just asking us for the number. It's not asking us for if we, take a random arrangement of 3 books from the 7, what's the probability that something will happen. So we don't have to divide this over a total. We can just say, oh, the total number is going to be 210 because we're taking books one at a time and placing them onto this shelf. So that's a pretty, basic permutation kind of problem. Let's do one that's a little bit trickier. Let's say now I want to take a permutation at random from the letters that make up the word sequoia. So S-E-Q-U-O-I-A. Okay. So I'm going to take a permutation. It is going to be a permutation of all the letters, all 7. And what we're going to do is we're going to say, what's the probability that Q is the 4th letter in our permutation that we take at random, and it ends in a vowel. So now we actually have a couple of requirements that we have to satisfy. But once again, it's a permutation, right? We're interested in taking these elements of the set and just rearranging them, right? So we're putting stuff into 7 different buckets. Okay. Now we know that Q has to go into the 4th one. So there's only one possible thing that could go into Q that satisfies our condition. And for vowels, there's 1, 2, 3, 4, 5 vowels that can go in this spot. So after we've selected our Q and our vowels, we only have 5 letters left, which means we then do the same thing we did for the bookcase. So we take one of them and put them here from among the 5, and then 4 we have to choose from to put here. Then we need to choose another one from the remaining 3 to go here, another one from the remaining 2 to go here, and the last book, or the last letter, sorry, will go here. And again, you can just multiply all these things together, and when you do, you end up with 600. So that's the number of ways that you can make permutations where Q is the 4th letter and it ends in a vowel. But unlike the book problem, which was just asking for the number of ways, this actually wants to know about the probability. So the probability, remember, from our previous video, is equal to the number of events that satisfy our condition divided by the full sample space, the number of events in the full sample space. So here we're going to have 600 is our number of permutations that satisfy, divided by the total number of permutations we could have, which we could do just like the book example, where we have 7 to choose from here, and then 6, and then 5, and then 4, and then 3, and then 2, and then 1. So when we do that, we multiply and just kind of decrement as we go. 7 times 6 times 5 times 4 times 3 times 2 times 1 can also just be written as 7 factorial. Okay? In case you haven't seen a factorial before, n factorial just means that we have n times n minus 1 times n minus 2, and so on, until you get to 1. Okay? So that's what a factorial is. So we have 600 divided by 7 factorial, and when we do that, we end up with 5 over 42. After simplifying, you get, this is 5,040, and that comes out to be about 12%. So there's a 12% chance that if we take a permutation at random of 7 letters from this word, we will end up with Q being the 4th letter and ending in a vowel. Okay, so now let's look at another word, which is going to complicate things just a little bit more. Now our word is going to be Mississippi. So the thing that makes Mississippi a little bit trickier is that there are repeat letters, right? We have 4 S's, we have 4 I's, and we have 2 P's, okay? So let's say now for Mississippi, I want to know what's the total number of permutations of Mississippi, okay? Now, we might be tempted to say, well, Mississippi has 11 letters, so we can go and make 11 slots and then just fill them in and do 11 factorial, right? We can do 11 times 10 times 9 and so on. But the issue is that some of these permutations are going to actually be identical, right? If I say that this is S1 and this is S2, then it's going to treat permutations where I have S1, S2 as different from those that have S2, S1, which they're not actually different because these are not really S1 and S2, they're just both S's, and they're interchangeable and they're identical. So what we have to do instead is say, okay, well, we know the total number of permutations we could have, that what it thinks we have, is 11 factorial. But we have repeats, and what we need to do is divide out all of the possible repeats and get rid of those. So ways that we can do that is we say, well, we have 4 S's, so how many different ways can we arrange S's? We can arrange S's by 4 factorial. There's 4 factorial ways to arrange S's. Same thing for I's. There's 4 factorial ways to arrange I's. And for P's, there are 2 factorial ways to arrange P's. Okay? So all we're going to do is just divide by all of the repeats, and the number of repeats they have factorial, I guess, if that's a word. So then you end up with 34,650 different permutations. This number, not super important. What's important is this process where you take all the duplicates and say, 4 S's, 4 I's, 2 P's. And then you need to get rid of any kinds of duplicates they're going to cause, and you can figure that out based on the fact that, hey, if I have 4 of them, the number of different ways I can arrange 4 S's is 4 factorial. So that's what we're going to divide by. There's going to be that many permutations of the word where S's are just repeating themselves, and you're getting the same permutation again with the same S's. And that's about it for permutations. So permutations, remember, we'll talk a little bit more about how to distinguish them from combinations in a bit. But in permutations, order matters, arrangement is important, and also permutations kind of have this sense of you're putting things into buckets. You're taking something and sorting it, right? You're sorting it into different slots, which is sometimes a helpful way to think about permutations versus combinations. So combinations is a subset of elements without regard to arrangement. So order does not matter when you're doing combinations, which means that what we need to do is we need to do kind of what we did for the word Mississippi, where we're going to take, to figure out what a combination should look like, the total number of permutations and divide it by all of the repeats. So the number of permutations of each one combination. Okay. Now, we didn't really use it. We didn't really need it for the last one. But there is, a formula that you can use for permutations if all you're trying to do is arrange R items from a set of N items. Some of the permutations we did, that's not what you're doing quite exactly. So you're not going to want to apply it. But if all you're trying to do is arrange, like the first problem, the bookcase problem, right? You have 7 items. You want to find how many ways can I arrange 3 of them. Then what you can do is you can use this notation of NPR, which is equal to n factorial divided by n minus r factorial. And this is the number of ways to arrange a subset of r items from a set of n items. Okay? So if we want the total number of permutations, we want to divide out the number of permutations of each one combination. We're going to have NPR divided by RPR. And if you go ahead and you plug these things in and you do it out, you end up with the equation for the combination, or N choose R. And the combination, so this is all of the possible arrangements where, we're ignoring the order, right? So we're getting rid of things that have the same order. And that's going to be NCR is n factorial over r factorial times n minus r factorial, okay? And just to expand on this a little bit more, so a permutation, right, is going to count, if we're just, have two elements, 1 and 2, it's going to say that 1 and 2 is a different arrangement than 2 and 1. Combination doesn't care about order. Combination is like, okay, I have a bag of items, I pull 2 out, what's in my hand? Whether I have 1 and 2 in my hand or 2 and 1 in my hand, I have the same elements in my hand, and that's all that combinations care about, okay? So what we want to do is, that's what we're doing, is we're dividing out any of these kinds of duplicates that permutations recognize are different, but combinations don't care about, okay? So that's what a combination is. Just briefly, I want to show you some of the notations that you're going to see for combinations and permutations. I'm going to generally stick to this one, but for combinations, you could see NCR, you'll see NPR for permutation. For combination, you could also see this. Permutations, you could see this. You could also see, what else? C and R or P and R. And then just for combinations, the worst notation that you can use is this one, where it looks like it could be a vector or something, and then that's just terrible. So I don't like this notation. But these are all notations that you could see in textbooks or in other videos, so just a good thing to be aware of. Additionally, your calculators, if you have a graphing calculator, do have functions that can calculate factorials, combinations, and permutations. You just have to go to the math button and then go over to probability, and you can select what you want. When you're inputting into your calculator, sometimes it's a little unintuitive. If you want to do, say, 3 choose 2, the way you're going to put this into your calculator is go 3, then go over, find the button, hit enter on NCR, and so it'll say NCR if you have a TI-83. If you have a TI-84, it will automatically take the 3 and put it into the N slot, and then you'll put in the second number, so 2, and you'll hit enter, and it will give you 3 choose 2. Okay? Now, there's also a quick and easy way by which you can figure out combinations if maybe you don't want to do it on a calculator. And that is with Pascal's triangle. So Pascal's triangle, some of you might be familiar with, is a triangle of numbers that you get by adding up the 2 numbers above it for each of the elements. Pascal's triangle is incredible. It has so many patterns. There's so many cool things that you can do with it or derive from it. And this just goes on forever. But for our purposes, what we can use Pascal's triangle for is we start with this is the 0th row and the 0th column. And if you do that, this is actually a triangle of combinations, where you could just write this as 0 choose 0, 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose 2, 3 choose 0. I mean, you get the idea here. Where all of these things all map to these over here. That's kind of a mess, but you get the idea. So if you're doing 3 choose 2, then you go 0, 1, 2, 3, 0, 1, 2. 3 choose 2 is 3. 5 choose 3. You're going to go 0, 1, 2, 3, 4, 5. You can always find it just because the first term is going to be the one you're looking for. And then 0, 1, 2, 3. So 5 choose 3 is 10, and so on. So just kind of a handy thing to keep in mind if you feel comfortable with Pascal's triangle, if you've seen it before. Then it's a nice little device that you can use. So let's look at some combinations. So let's say that I have a group of 9 people, okay? And what I want to do is from those 9 people, I want to form a committee of 5 people, okay? I want to know how many ways can I form a committee of 5 people from a group of 9 people? How many different ways? When you're doing this, you have a group of n and you want to make a group of r from that, and you want to know how many ways you can do it. You're literally just plugging in to the combination, because that's what a combination is, where you're just doing 9, choose 5. Even the way you read it off makes it exactly what you want to do for the problem. You have 9, you're choosing 5. How many ways can I do that? You can use Pascal's triangle, or you can put this into your calculator. You should end up with 126. So that's just like, very base level combination. And already, too, you can see what I referenced earlier where I mentioned that permutations, you tend to be taking things and putting them into buckets, whereas in combinations, this is another way to tell them apart, in combinations, you're really pulling items out of some kind of bag and putting them into just a smaller set, right? You're taking like marbles out of a bag versus taking a bag of marbles and then splitting them up into other little mini buckets, right? So just kind of another way to think about combinations versus permutations. Okay, so let's do some more combination problems. We're going to build on the building a committee of 5 from 9 people, but now what we're going to do is we're going to split up the people a little bit. I'm going to say I have 9 people, and I have 6 women, and I have 3 men in my group of 9. And I still want to form a committee of 5 people. Okay, we're going to do 3 different things here. So I want to know what's the probability that for the first one, let's say, what's the probability that I choose 2 people who I'm going to name Aileen and Ben. And I want to know how likely is it that if I form a committee of 5, I end up with Aileen and Ben on my committee. So what we have to do that is, for probability, remember, we're doing the number that satisfy our requirement divided by the total number available in the sample space. So we already said that the total number, for all of these problems, n of s, if we want to set up a committee of 5 from 9, is 126. So we're going to be dividing whatever number we get by 126. So what we are going to do when we do this is, first, we're just going to say, if I want committees, how many committees exist with Aileen and Ben on them, I'm putting Aileen and Ben on them. So I'm first choosing Aileen and Ben. So first, choose Aileen and Ben. And once I have them on my committee, I only have 3 slots left, right? So if I have 3 slots left and I've pulled 2 people out of the pool of 9 that I started with, then what I'm doing is I'm choosing 3 people from among the remaining 7, okay? So the second thing we want to do is choose 3 more people to fill the committee from the 7 that are remaining. Remember, it's 7 because we already pulled Aileen and Ben out, which means that what we are going to end up with is we're going to have the number of events that satisfy our requirement is just going to be 1, because there's one way to choose Aileen and Ben. There's only 1 Aileen and 1 Ben, times 7 choose 3. And this gives us 35. Again, you Pascal's triangle, calculator, whatever. And then we can find the probability by saying we're going to take 35, we're going to divide it by 126. When you do that, you get 28%. So around 28%, a little under a third of our committees that we make will have Aileen and Ben on them. Okay? So let's make this a little trickier again. I'm just going to kind of be elevated. We're going to do 2 more of these. Let's say now I want exactly 3 women and 2 men on my committee of 5. How do I do that? So if I want 3 women and I want 2 men, there's kind of a hidden and in here, right? So I'm doing both of these, and then I get to multiply the probability together. Whenever you're given something like this that has multiple requirements or multiple parts built in, a nice way to do it is to break it down into pieces, and then add or multiply as appropriate. So we're really looking for 2 things. 1, we're looking to select 3 women. So how do we select 3 women? Well, there are 6 women total, and we're choosing 3. So we're going to do 6 choose 3. That's going to be the number of ways that we can choose 3 women from 6 women. Second, we need to select 2 men. We're going to do the same thing for the selecting 2 men. There are 3 men total. We want to choose 2 of them. So now we have the probability that we can pull, or not the probability, sorry, the number of ways that we can pull 3 women from 6, and the number of ways that we can pull 2 men from 3. If we want both of these things to happen, we want this and this, we multiply. So we have 6 choose 3 times 3 choose 2. Once you've done that, we say, okay, this is just going to be 20 times 3, which is equal to 60. And then we divide 60 by our total, so we have 60 divided by 126, and that gives us about 48% chance that if we make a random committee, we'll have 3 women and 2 men. So again, when you have this complicated stuff where it's multiple pieces kind of smushed together, what you want to do is split it up into things that you can calculate and then combine those as is appropriate with addition or multiplication. Remember that and implies multiplication or implies addition. So the last one we're going to do is we're just going to say, what's the probability we have a committee with at least 3 women? Okay? Now, when you see at least, this secretly is an or, right? This is saying the probability that you have 3 women, or you have 4 women, or you have 5 women, right? That's what at least means. So what we're going to do is we're going to calculate each of those. We're going to say, what's the probability that I have 3 women and then 2 men? What's the probability that I have 4 women and 1 man? Or what's the, not probability, I keep using that word. What's the number of ways that you can have a committee with 4 women and 1 man? And then what's the number of ways you can have a committee with 5 women and 0 men? So once we have this set up with, okay, we know what we want to do, we're going to do each of these like we did part B here. So 3 women and 2 men, we already calculated. This is going to be 6 choose 3 times 3 choose 2. This one, 4 women and 1 man. For this one, we're just doing 6 choose 4 times 3 choose 1. And then for the last one, we're doing 6 choose 5 times 3 choose 0. And then because it's ORs, we're adding them all together. So this is 60, we already calculated that. This is 45, we have 15 times 3. And this is 6 times 1, which is 6. So then we have 60 plus 45 plus 6, and that equals 111. And then if we want the probability, we can take 111, divide it by the total, which is 126, and then we get around 88%. So 88% of our committees will have at least 3 women if we're choosing them from this pool of 6 women and 3 men. Okay? So, these are kind of how you want to approach problems with combinations. Combinations, you're always generally going to use this, 7 choose 3 equation, which, as we wrote up earlier, if you have NCR is equal to n factorial over r factorial n minus r factorial. And whereas permutations, there's a little bit more diversity in the kind of problem that you're doing. The 2 ways, to summarize here, the 2 ways to distinguish between whether you want to use a permutation or you want to use a combination is the first way. Permutations have an arrangement, they have an order. The order matters. Things that, even if you have the same object, but they're in a same set of objects, but they're in a different order, then, permutations are going to count that differently. Combinations do not care about order. Whether I have, red, blue, black, or black, blue, red, combinations don't care. Combination says, oh, that's the same combinations of, colored marbles that are in your hand. Second way to kind of think about it is, are you splitting things up into different categories or different buckets? If you are, you're probably doing a permutation. Or if you're just pulling items out of a set of other items and saying how many ways can I pull things out, that's a combination. If you're pulling stuff out, it's going to be a combination. If you're splitting stuff up into buckets, it's going to be a permutation. So that's pretty much it for permutations and combinations. Hopefully that is helpful, and next time we're going to be doing some more probability. Thanks for watching.